great. So now we got a quorum. So let's get started. Cool. So algebra expressions. This starts off by talking about things to do with word problems. Like I said, there's an infinite variety of word problems on the GRE. If they're not your thing, if you really have a hard time with them, there's a few types that you ought to know how to do, but I wouldn't spend too much time on them if you're short on time to study, because it's very difficult to learn how to do all word problems. And so you could spend a lot of time on them and still get one on the test that you're just not sure how to do it. So I don't know that it's the best play, but some people just really have a knack for them. That's great if you do. This is variables. This is basically telling you that when you get a word problem, the first thing you do is define your variables. And it's a really smart idea when you're defining your variables, not to just use X and Y. You're talking about motorcycles, use an M. If you're talking about cars, use a C, that kind of stuff, okay? Expressions and equations. An expression is just something that doesn't have an equal sign in it. The thing about expressions is that they can't be solved. They're not equal to anything. They can't be solved. So about the only thing you can do with an expression is multiply by 1. And when I say that, that's like when you do the thing, like sometimes it's helpful in an expression to multiply by 2 over 2 or root 2 over root 2 or something crazy like that. But with expressions, you cannot solve them. If there's no equal sign, you cannot solve them. If there is an equal sign, you can solve them. And this is where the rules of algebra work. And this is awesome because you can do anything pretty much to this equation as long as you do it to both sides. You can multiply by things, divide by things, whatever you want to do as long as you do it to both sides. The order in which you solve an equation, you try to get rid of any fractions, you add or subtract everything you can to get the target variable on one side, then you factor out the target variable, then you divide by everything else. Essentially, you work from the outside in to isolate a variable. Okay, so for example, this is not what we wanted to say. Not sure what that is supposed to say. Let's just forget about that. Let's say this is supposed to say P is equal to 1 plus 5 over Q plus 2. We'll just say that, okay? So let's say we have this thing here. P is equal to 1 plus 5 over Q plus 2. First off, is this an expression or is it an equation? Expression or equation? It's an equation, exactly. It's got an equal sign in it. Okay, so how do we solve it? Well, the first thing we do is we multiply by Q plus 2 to get everything out of the denominator, get rid of fractions, particularly get rid of fractions when they're variables in the denominator. So if we do that, we get P times Q plus 2 is equal to 1 plus 5 over Q plus 2 times Q plus 2. So we've just multiplied both sides times Q plus 2. We can do that as long as we do it to both sides. These Q plus 2's cancel each other, right? Okay. So what are we left with now? We're left now with P times Q plus 2 is equal to 1 plus 5. Okay, so now what do we do? Well, I'll probably want to distribute out this P. So then we get PQ plus 2P is equal to 1 plus 5. And if we're solving for Q now, we want to get Q alone. So to get Q alone, we're going to work from the outside in. So we're going to first off get rid of the terms that aren't connected to it. So in this case, the 2P, we can subtract that from both sides. And at this point, I'm going to combine this to make 6 because I'm tired of rewriting it. So we get PQ is equal to 6 minus 2P, because these 2P's canceled. Now, to get Q truly alone, now we have to deal with the things that are attached to it. So now we're going to divide by P. So now we're left with Q is equal to 6 over P minus, now we've got, remember that we could have 6 minus 2P, or that you could rewrite this as 6 over P minus 2P over P. That would be the same thing. You can either put one big P on the denominator here, or you can split it up into two fractions. Okay, so with 6 over P minus 2 over P. You can rewrite the P if you want to or not. It means the same thing. So I'm going to split them up, and I'm going to say it's equivalent to 2 minus 2P over P. So again, I've split up the P. But now the P's cancel. So now I get Q is equal to 6 over P minus 2. And that would be my answer. Okay. So that goes through all the different processes that you might need to do to get a variable alone. Okay, that's how you solve for a single variable. You try to get things out, get the fractions out of there, and then work from the outside in towards the variable that you want to solve for, okay? All right, so this is not a problem we're going to do tonight. That's an okay problem, but not really worth doing. Okay, so we get on to systems of equations. The systems of equations are very, very common on this test. You can see a lot of different types of them. Like I said, the most common types are the age problems. Those are really common. And then there's also the ones involving the prices of hot dogs and hamburgers, or you sold a certain number of things. There's two really good ways to solve systems of equations. There's substitution, and then there's combination or elimination is the way you other call it. I call that the stack and add method. Okay, so both of those are good. Depends on the situation. I tend to use elimination a lot just because I think it's cool, but it's definitely not the only way to do it. The reason we would need to use one is if we have two variables and we need to solve for both. So let us go to an example here. Solving equations for multiple variables. So we got to solve for two things at a time here. Now we have 2x is equal to 3y and x plus 5 equals 2y. There's no way to solve this equation for x because we don't know what y is, right? But if we know, and the way to think about this graphically is if you plotted this, it would make a line. There'd be a value of x that would give you a value of y, and then a different value of x would give you a different value of y, and a different value of x would give you a different value of y. And what you would make basically is a line if you were to graph the answers. Okay, so every x value would have its own y value. Now, that's an infinite number of solutions. If you have two equations, then the other equation is going to make a line too, but the line will be a different line. And where they cross, that's what you call the solution. So that's the solution. And that is the point, the value for x and y that makes both equations work. Okay? So there's lots of different x's and lots of different y's that can make this work, and lots of x's and y's that could make this work. But there's only one that will work in both equations at the same time, one combination. All right? Cool. So if you know how to solve this, great. Go ahead and do so. I'll give you a minute to go for it. And at the end of a minute, I'll show you how I would do it. Okay? So take a minute here and see what you come up with. And then I will show you what I will do. Okay? And your time starts. Oh, I need my watch. Hold on. Your time starts now. Okay, so that's a minute. This here is an example of a good opportunity to use the substitution method. When we say substitution, what we mean is that we're going to substitute a value of x in for y, okay? And we've got some directions on what to do here. The first thing I'm going to do is I'm going to solve for x in the second equation. So when we do that, we get so we start with x plus 5 is equal to 2y. And if we solve for x, that means get x alone. So subtract 5 from both sides. And we're left with x is equal to 2y minus 5. Okay, so we solve for x. Here's where the substitution piece comes in. So this means that anywhere we have an x, we can substitute this in instead. What's great about that is that now we're going to replace x in the second equation. Sorry, in the first equation. I think that should say first. In any case, that'll work. Okay, now we're going to take this value of x and we're going to substitute it in for the first equation. So that equation used to be 2x is equal to 3y. And remember, that has two variables in it, so it can't be solved. But now we can take this that we found and plug it in wherever x is. So where that x is, I'm now going to put in 2y minus 5. Okay. Now I'm going to distribute. Okay, let me erase this actually just so that we can make more space here. Okay. So now I'm going to start solving for y. Okay. That'll give me 4y minus 10 is equal to 3y, right? If I distribute out here, distribute the 2. Okay. Now if I subtract 4y from both sides, these will cancel. I'll get minus 10 is equal to a negative y. Or in other words, 10 is equal to y. Great, I found y. I know what y is. This is the value of y that will be true in both equations. Okay, good. It looks like Hema has one. Awesome. Hema's got a solution. Okay, so, but this is why they're wanting me to find x. That's fine. I just take this value of y now and I can plop it into either equation that I want. It doesn't matter, but I'm going to pick the first one because it's shorter. So now I'll go 2x is equal to 3y, but I know that this y is 10. So 2x is equal to 3 times 10. 2x is equal to 30. So x is equal to 15. So Hema, exactly right. Y is 10 and x is 15. Okay. So this is an example of the substitution method, meaning you isolate x in one equation. Whatever that answer is, you plop it in to the other equation. Okay, substitution method. There's also something called a combination or elimination method, otherwise known as stack and add. Okay, so here, and this could be solved the other way. That's absolutely fine, but I'm going to show you a second way. So here we've got this thing here. X is equal to y plus 6 and minus 2x is equal to 2y minus 7. So the first step, I think, is you write them on top of each other. And the reason I say that is because we are going to be, I don't know if you can do this, but you can add straight, right? So we can add these together and we get a minus x is equal to minus y. 6 minus 7 is a minus 1. So x minus 2x is minus x. Y minus 2y is minus y. 6 minus 7 is minus 1. So you can add those together. That's just something you can do in algebra. What's even better than that, though, is that, remember that my problem is I've got two variables in these equations, and I can only solve for one at a time. So another cool trick I can do is I can look at my variables and say, when I add these together, nothing cancels out, but let's just say equals, right? Yeah. But if I multiply this guy by 2, I'm going to multiply this by 2 up here, okay? Then what I'm left with is 2x is equal to 2y plus 12. And I'm not going to touch this. I'm going to leave that just like it was. Okay. Okay, so I haven't touched this bottom equation, but on top I've multiplied by 2. Now, why did I do that? Because now when I stack and add, some of my variables are going to disappear. Because when I add these, 2x minus 2x, I'm left with just 0, right? The x's are gone. And then here I have a 4y, and here I have 5. Look at that. Now I have an equation I can solve because now there's just a y in it. I add 5 to both sides, get 5 is equal to 4y. Divide by 4, divide by 4. Y is equal to 5/4. Now, if I want to know what x is, I just plug it into one of these, okay? So I'm going to go here. I'll take that first one. So we know that x is equal to y plus 6. But now I know that this y is actually 5/4. X is equal to 6 plus 5/4. That's your answer. Okay, so this is the elimination or stack and add method. This is kind of weird that it works out as a fraction. Typically, if you're doing the problem right, they'll make it work out evenly so that you don't get a weird number. I think that makes this look like a more off-putting method than it really is. It can be really clean to do a problem like this where you just like stack them up, add, and a variable disappears. Okay, so those are your two options. When you got a system of equations, in other words, you have to solve for more than one variable at a time, either an x and a y or an x, y, and a z. You can use substitution or you can use elimination. All right, so here we have an example of a word problem that's going to take two variables. So we know it's going to be a system of equations. So our system here is going to be, first off, we need to define our variables. Okay, so step one is always define variables. Okay, if you don't know what your variables are, try what they are asking for. Okay. So, Edward is twice as old as Julia. If in 20 years, Edward will be 5 years older than 3 times Julia's current age, how old is Julia now? Okay, that's a big, long, ugly sentence, right? What are our variables? We'll just start there. Just start with what are our variables? Yeah, Julia and Edward's ages. Nice, exactly. Okay, cool. So we want to be very clear in these. This is the most common mistake that people make, is that they don't keep track of their time frames. Okay, so let E equal Edward's age, and I'm going to say now. Let J equal Julia's age now. And the reason I say that is it can be very tempting in these problems where they're saying 20 years from now to just use E again. Edward's age is E. His age in 20 years is going to be E plus 20. Okay, or whatever other, oh, that's weird, whatever other time frame shifts they need, okay? But just keep track of that. That's where people tend to go wrong. They make E Edward's age and also E Edward's age 20 years from now. That can't be. Okay. All right, so Edward is twice as old as Julia. Okay, so how can we write that in algebra? Edward is twice as old as Julia. E equals 2J, totally. E equals 2J. I guess I should do this. Sorry, my caps lock's on. E is equal to 2J. Okay. Okay, next sentence. That's great, but that has two variables in it. We can't solve that. We need another equation. If in 20 years, Edward will be 5 years older than 3 times Julia's current age, how old is Julia now? Okay, let's just work through that piece by piece. That's a long sentence. So in 20 years, Edward. So we know that we're dealing with Edward's age plus 20 years. Okay. He'll be 5 years older than 3 times Julia's current age. So how could we write that part? 5 years older than 3 times currently Julia. Yep, totally. Yep, we're going to do 3 times Julia's current age plus the extra 5 years. Okay. Remember, we want to add 5 years older. He's not going to be 5 times older than 3 times Julia's current age. He'll be 5 years older. So we're going to add 5. Okay. And we're trying to find J. Okay, great. So now we have our 2 equations. What do you want to use? Substitution or elimination? Substitution or elimination. Those are your 2 equations. Substitution, yep. Substitution would be a much better choice here. Good, Hema. Cool. So here E is equal to 2J. Perfect. Well, I'm just going to take that 2J and put it down here where the E is. So I get 2J plus 20 is equal to 3J plus 5. Well, great. Now I just have one equation and it only has J's in it. And that's perfect. Okay. So get all the J's together on one side. Okay. So just subtracted 2J on both sides. These canceled. So I'm left with 20 is equal to J plus 5. 15 is equal to J. So now I found this number. In the last step, the other place that people tend to go wrong is they get a number, but then they don't check that it's actually what they were asking for. So 15 is Julia's age now. And so I want to check, is that what they're asking? Ah, how old is Julia now? Great. Okay, so 15. Julia's 15. So the answer is B. Okay, so this is a type of problem that's worth knowing how to do just because age problems are very common on the test. And there's a limited number of types of age problems, so these are worth knowing. This one we skipped over a problem involving hats and shelves. This is a more difficult level problem. So this is a 160-ish problem, okay? And it's a little bit different and weird. So if you're feeling confident on your word problems, you can come back to this guy and check it out because this is less, it's just a little bit out there. It's a little bit anomalous as a problem, okay? But that's a good one, okay? The age problem stuff is much more standard. Okay, FOIL and factoring. So some of you folks got to see this over the weekend, FOIL and factoring. FOIL is what we do to, what we say, expand expressions that are in this form. So we'll see something like x plus 2 times x minus 5, for example. And we want to expand that, meaning get rid of the parentheses. And in order to do that, we use the acronym FOIL, which means we multiply the first terms together. Okay, and that gives us x squared. Then we multiply the outside terms together. And that gives us a minus 5x. Then we multiply the inside terms, and that gives us a 2x. And then we multiply the last terms. That gives us 2 times minus 5 is minus 10. You can always combine the middle 2 terms here. So we get x squared minus 3x minus 10. So that's what FOIL is. It takes you from something in this form with 2 sets of parentheses to something in this form, which has a square, an x, and a constant. Okay? So that is FOIL. Cool. So expand this guy using FOIL. Go for it. Yeah, nice, Nike. That looks good. Okay, so Nike has given us x squared plus 4x minus 12. I think that's right. So we multiply our first terms together. That gives us x squared. We multiply our outside terms. That gives us 6x. We multiply our inside terms. That's minus 2x. We multiply our last terms. That gives us minus 12. These two combine. And that gives us x squared plus 4x minus 12. So nice answer, Nike. Okay, so what do we do when we have something that's a little longer? The same rules apply. There's just not a cool acronym for it. The rule is basically just multiply the first term times all 3 and then the second term times all 3. Okay, So if we multiply the first term times all three, we're going to get an x squared for the first one, plus an xy for the second one, minus a 2, or minus a 2x for the third one, because it's x times minus 2. Okay. Now we're going to move to the 1. Okay. For the first term, we're going to get just an x, or a 1x. For the second term, we're going to get 1 times y. So that's just a y. And for the third term, we're going to get a minus 2. In other words, we're basically just getting an x plus y times a minus 2 because we're just taking everything in this parentheses and multiplying it by 1. Okay. So now we've got this whole ugly thing, and we see if there's anything we can combine. The only thing we can combine actually is these two x's. So we're left with an x squared plus xy minus x plus y minus 2. Okay. And again, all I did was I multiplied the x times all three terms, and then the 1 times all three terms. And you add up, and the only terms you can combine are the x's there. Okay. Cool. All right, so then we get into various types of factoring. So what we just did was expanding. It's unfactoring, kind of, okay? When we factor, we go the other way. So we take something that looked like this, or looked like those binomials, and bring it back to this parentheses state, okay? The most common type is called factoring by common terms. Factoring by common terms means you take a number and you pull out the biggest thing you can pull out. And I think we talked about this with those exponent problems, pulling out 3 to the 20th, that kind of stuff. Okay. In this example up here, if you wanted to go from 2x plus 6 and factor it, you would pull out a 2 because that's the biggest number that you can pull out of both 2x and 6. And you get 2 times x plus 3. This would be an example of factoring by common terms. Okay. So, oh, this thing again. Gosh darn it. This is such a pain. Let's just say this is, let's say this is a 2 and this is a 3. Okay, so this is a 2 and this is a 3. Okay, I'm going to cross this out so it's a little better even. It's hard enough to do them when the exponents look neat. Okay, so let's say we have the numbers negative 5x squared minus 25x cubed y, and we wanted to pull out the biggest term that we can pull out. What is the biggest term that we can factor out of this expression? Okay, so we can pull out a 5. Now here's the thing, Hema. You can also pull out letters, right? Okay, so cool. So Hema's seeing 5, and we can definitely pull a 5 out. We can pull out an x squared. Nike says we can pull out an x squared as well, and we can pull out an x squared, but we're not done yet. There's one other thing that we can add in there that we can pull out. We can get the y too, right? There's a y on both sides. Okay. Yeah, just the y. We can't pull out a y squared because we can only pull out something that's in each term individually, okay? And so neither of these terms has a y squared in it. They just have y's in them. So we can only pull out y's. Yep. Okay, so that's fine. So what are we left with? If we factor minus 5x squared y, sorry, if we factor 5x squared y out of minus 5x squared y, what are we left with? It's kind of weird. What are we left with? Yeah, Nike, exactly. We're left with just minus 1. That's it. And we can check ourselves if we're not sure, because if we multiply this times this, we should get our original number back. Okay, so that's what we're left with. Okay, and what about when we factor it out of the second term? So we're pull the 5x squared out of this second term. What are we left with? We're left with, so we pull out a 5 from minus 25, and we're left with minus 5. We pull out an x squared from an x cubed, and we're left with x. We pull out a y from a y, and we're left with nothing. So it's just minus 5x, right? So just to say that again, we're going to Pull the 5 out of the 25. So we're left with minus 5. We'll put the x squared out of the x cubed. That gives us 1x that's still left. And the y out of the y, that means the y is gone totally. So we get minus 1 minus 5x. Yep. Yep. Cool. So that's an example of factoring out common terms. We pulled out the biggest term we could pull out there. Now, factoring by grouping is a little bit different. I think this is supposed to be a 3 and this is supposed to be a squared. Not totally sure, but I think so. Okay, so factoring by grouping. This is kind of contrived. So the idea here is we are going to look at this and say, wait a second, there's nothing that I can factor out, right? I can't factor out an x from everything here, right? Because this 6 doesn't have an x in it. I can't factor out a 2 from everything here, or a 3. There's nothing I can factor out of every term. But there's still something you can do. You can split them in half. So let's just split this to be x to the third minus 3x squared. Okay. And then we'll keep this as 2x minus 6. Okay. Now, what can I factor out of this first pair, this first parentheses? Totally, we can factor out an x squared. But we can't factor out x to the third because that's too big. We can't, x third won't come out of this one, okay? So, but we can get an x squared out of both of them. So that leaves behind an x minus 3. Okay. And then what can we factor out of the second set of parentheses? We kind of did it on the last slide, I guess, but yeah, we can factor the 2 out. Perfect. Okay, so these tend to be very contrived problems for the following reason. What you'll notice now is that we have in both cases this x minus 3. Okay. So the way that factoring by grouping works is we're going to take that x minus 3, and that's one of our pairs. And then our other pair, as you may have guessed, is going to be whatever the coefficients are for the brackets, okay? So it becomes x squared plus 2. Okay? So this only works if you get a situation where when you factor out the numbers, you end up with the same thing in the parentheses for both sets, okay? And in this case, we got x minus 3 on both sides. We're good. That's going to be our first set. And then our second set of parentheses is just whatever is left over in the coefficients, okay? If the x minus 3s weren't the same, we'd be out of luck. Okay. But because this is the GRE and the problems are carefully crafted, you could see something like this. So that's called factoring by grouping. This here is kind of like the factoring that we practiced over the weekend, okay? So actually, let's not do this one. I don't know why that one comes first. We want to do this guy first. Okay, this is x squared minus x minus 6. That's what we want to factor, okay? X squared minus x minus 6. There's some, like I said, there's something weird that happens where some of these symbols and exponents turn into other things. Don't look at that. That's too scary. That's not supposed to be that scary. That's just like the embedded font's not working, okay? So what we really want you to do is factor x squared minus x minus 6. Okay, what does that factor to do? Okay, and again, this is like the type that we practiced over the weekend if you were part of that session. What do we come up with? So remember how this works is we're going to look for factors of 6 that have to add up to the coefficient of this number. Okay. Really close, Lauren. Okay, so our factors of 6 are going to be 6, 1, and 2, and 3. Yep. And remember that we know that it's a -6, so one of these is going to be positive and one of these is going to be negative. And we need to pick the combination that gets us a -1. Okay, so Lauren, you're really close. Yeah, there we go, Nike. Yep, exactly. Okay, so our factors of 6 that are, yeah, there we go. Nice. Yes, good, Hema. That's right. Yep. Okay, so our factors of 6 that we're going to use the 2 and the 3, right? Because they're the ones that have a difference of 1 between them. And which ones are we going to use? We're going to use the -3 and the +2 because we want them to add up to a -1. Okay, so it's x minus 3, x plus 2. Very nice. So this is what happens when you have a situation where there's nothing in front of that x. This is a big old blank. There's nothing there. Okay. There are also problems where you have a coefficient on that x. Like here we have 3x squared. These are a little bit different. Okay. When you have this situation, set up your parentheses the same way. And we're still going to try to find factors of this 4. But now we're going to play a little bit of a different game that sometimes involves a bit more trial and error. So first off, our factors of 4 are going to be 4 and 1 and 2 and 2. We know it's a -4, so one of them is going to need to be positive and one of them is going to need to be negative. Okay. But instead of just picking the factors that add up to make 4, we have to take into account this coefficient that's there now. And the way it works is we're going to multiply this number times this number and add this number to make 4. Okay? So rather than just this number times this number, or rather than just the factors that add up to 4, we're going to be multiplying this number times this number and adding this number to make 4. So with that said, I probably don't want to pick the 4 in one set, because if I put a 4 over here and I multiply by 3, I'm going to be way up in the 12s, and that's probably going to be too high for me, so I don't want to do that. And if I put the 1 there, then it's going to be 3 times 1 plus 4, so that's going to be like, I don't know, that's going to be like 7 or something. That's not going to be right. So I'm going to be working with this pair here, and I just need to decide which one's going to be positive and which one's going to be negative. Okay. And since I want to end up with a positive 4, I'm going to try both ways, but let me try +2 and -2. So I'm going to pick the positive 2 is going to be in this spot, and the -2 is going to be in this spot. Now if I do this, I get 3 times 2 is 6, -2 is 4. So that's what we want. Okay. So again, this one times this one plus this one has to equal that middle number. So 3 times 2 is 6, -2 is 4. So this is how I would factor the coefficient here. And you know, sometimes it just does involve a little bit of like trial and error. Sometimes you just got to fill your blanks. And I was telling the girls over the weekend that like, when I was first learning to do this, I would like erase holes in the paper because I would have to try different combinations and actually write them down and see them. And I didn't have a good intuition for what would work until I actually wrote it down. So holes in the paper. But anyway, so that is how you do these ones that have coefficients. Okay, so let me get to common patterns, and I don't want you to worry about these guys. These are not important. I do want you to worry about these guys up here. Okay, and this is called the difference of squares. And I'm actually just going to write over this so that it doesn't look terrible like that. Okay, so this guy here is called the difference of squares. The difference of squares is a form that you will see on the test that means you have two perfect squares that are being subtracted from each other. So in other words, the form you'll see it usually written at is a squared minus b squared. That's not terribly helpful. What it really means is something like, let's say you had x squared minus 4. X squared is a perfect square, and 4 is a perfect square, right? It's the square root of 4 is 2. You could also have something like x squared minus 9. Or you could have something like 4x squared minus 4, because 4x squared is a perfect square as well. That would be 2x would be the square root of the perfect square, or the root of that, okay? So these are called the different, it's called the difference of squares when you subtract a perfect square from another perfect square. The reason this is important to know is because these factor in a very predictable way. I'm just going to write them out here. Okay, whatever the square root of this guy is, you're going to add 1, you're going to subtract 1. So here the square root was 2, so that becomes x minus 2, x plus 2. Here the square root was 3, so we factor it as x minus 3, x plus 3. Here the square root is 4, but we've got this 4x squared, so this is going to be 2x minus 2 and 2x plus 2. The mathy way to write this is that you will see is a squared minus b squared is equal to the root of a minus the root of b plus the root of a minus the root of b. So it'd be like a minus b times a plus b. Okay. The reason I say you have to know this is because there are a few problems where you need to recognize the difference of squares in order to solve it. You just can't factor it any other normal way. Okay. You have to know that this can become this if you wanted to. Okay, difference of squares. Okay, questions on any of this stuff? Because I think we get it. Yeah, because we get to that problem. It's a great problem. Questions on any of this factoring stuff? Okay, we're going to jump into a difference of squares problem. I will point out, this problem is, you'll see that we start off with a w squared minus 2. That's not quite a difference of squares. Why not? Why is the w squared minus 2? This is not a difference of square. Why not? What is wrong? Why is w squared minus 2 not a difference of squares? Because the 2, yeah. Why? What's wrong with 2? It's not a perfect square. Perfect. Okay, it's not a perfect square. However, you will see in this problem that we have this 1 like wanging out here. If we add 1 to both sides of this problem, then all of a sudden these 1's cancel and we're left with w squared minus 1 is equal to w plus m times w plus n. Now, is that a difference of squares? That is a difference of squares. Totally, it is, because 1 is a perfect square. The square root is 1. Okay, great. Cool. You got a minute. You can do the rest of the problem. Okay, so that's a minute. And answers here. Let me get an idea. What is going on? Well, we've got w squared minus 1 is equal to w plus m, w plus n. Well, we know now that this is a difference of squares, and that's great. And a difference of squares tells us that that will factor to w plus 1, w minus 1. Because that's what the difference of squares does. Okay, that's how we factor it. We also know that it's the same as w plus m, w plus n. Okay. So we know then that m and n have to be 1 and minus 1. But the thing is, we don't know which is which, right? This could be w minus 1, w plus 1. We don't really know. It would be the same thing. We just know that it's got to be a 1 or a minus 1, okay? But we get one other hint in the problem, because it says that m has to be greater than n. So if we're solving for m, and we know that it has to be a 1 or a negative 1, it's got to be the 1, because it's got to be bigger than the other guy, and the other one's the negative 1. Okay. So if m is 1, then n is negative 1, and that's the only way that we're going to end up with n greater than n. So m is 1. Okay, and so this is the type of problem where you need to know the difference of squares, factoring, JAG, or you can't get this problem. Okay, so that is how this one's done. Okay, here is another one. I just want to make sure, hold on one second, that that's supposed to be 0 there. I can't recall if it is. Give me one moment. Yeah, we're good. Yeah, so that is supposed to be a 0. So this problem is correct as it is written. Okay, cool. How did I know to substitute m and n for 1 and minus 1? Okay, so in this problem, yeah. All right, because what we know from what we are given here, let's start up here. Okay, so we rearranged and we got that w squared minus 1 is equal to w plus m times w plus n. Okay. We also know that w squared minus 1 factors to make w plus 1 w minus 1. And the reason we know that is because of this whole difference of squares thing, that a squared minus b squared can be rewritten as a minus b times a plus b. So in our case, the w's and the 1's, you know, when we factor down w squared minus 1 with these two squares, we get w plus 1 w minus 1. So if we know that both of these are true, then we know that this has to be a 1 and this has to be a negative 1, or the other way around. Okay? Yeah. So the final step in this problem, so we know that m has to be a 1 or a negative 1, and n has to be a 1 or a negative 1, because that's the only way that w squared minus 1 factors, okay? Now, how do we know that m is a 1 rather than negative 1? Because they tell us that m is greater than n. Yeah, cool. Okay, great. You understand that stuff. Yeah. No, it's this part here. We know they're telling us in the problem that w squared minus 1 is equal to wn plus wn. And then we also know when we factor w squared minus 1 that it's equal to this. So we can just look at them and be like, oh, okay, well, then one has to be a 1 and one has to be a negative 1. Okay. Yeah, cool. That's it. Cool. Yeah, no, great. Thanks for asking. That's a little bit of a strange one. You got to sort of be like, but how do you know? And it's basically just because you do a matching thing. It's kind of like when you when the bases match, you just compare the exponents, that kind of thing. It's a little bit like that. Okay, cool. So now we get this one. We got to do some factoring. Okay, you got a minute and a half, and your time starts now. Okay, so I got at least one answer. So let's go through how to, oh, are we still, come on, come back screen. Okay, so with this guy, -2 is less than x is less than 5. Okay, so great. We see that we've got a quadratic on one side and 0 on the other. So your first instinct when you see something like this, okay, good, we've got an answer from Nike too. It should be to factor it, right? So we factor these. If we factor that, we're looking for factors of -10 that add up to -3. So we'd want to pick a -5 and a +2. So x could equal -2 or 5. Now, how do I know that? Because I'm looking for the sides of this one that equal to the values that we could plug in the parentheses that'll make 0. And so on this side, we would need a -2 to make 0, and on this side, we would need a +5 to make 0. Okay, these are factors here. Okay, so no, actually, yeah, sorry, that's actually not the way to look at it, but so and on this side we have 0. Okay, so what do we know? We know that if we put in a -2 on this side, like I said, we would get a 0. And if we put in a +5, we would get a 0. If we put in anything in between, well, we would have to check it out, right? So if we put in a -1 into this side, we would get a -1 and a -6, and that would give us a 6. If we put in a 4, for example, and I'm just trying the far extremes of what would be allowable here, a -1 would be the smallest really value, and a 4 would be the largest if we were dealing in integers. So if I put in a 4, I'm going to get a 6 times a -1, and that's going to give me a -6. So which one is bigger? Well, we can't tell, right? Because in one case we got a 6, the other case we got a -6. 0 is right in the middle, so the relationship cannot be determined. So answer D. Good answer, Ashmini. Good answer, Nike. Did you have to factor it? You don't have to. You can square if you want to. Okay. All right. So what do we do with factoring if we are going to solve? Okay. So far we've been dealing with expressions. We've been dealing with quadratics that do not have an equal sign. Okay. This one does have an equal sign, and very often people will look at an equation like this and they will try to isolate x. They will try to get all the x's to one side, and they'll very quickly discover that they haven't gotten anywhere. They still can't solve. When you see an equation like this, where you've got a squared term, an x term, and a constant, you should not try to isolate x. What you should do is get everything on one side together and factor. So here's what I mean. I'm going to, rather than try to get the x's here and the 15 over here, I'm going to get everything over. So I get x squared minus 8x plus 15. So everything's getting over to the left side, and all I'm left with on the right side is a big old 0. From here now, I'm going to factor. If I factor this, I'm looking for the factors of 15 that make -8. So I'm going to pick a -3 and a -5. Cool. So remember that to get a 0 by multiplication, one of these terms has to be 0, right? So either this parentheses has to equal 0, or this parentheses has to equal 0. So if I want this parentheses to equal 0, x is going to be equal to 5, right? And if I want this parentheses to equal 0, x is going to be equal to 3. So the two solutions to this equation are that'll make the whole expression equal, the whole thing equal to 0. I could have an x equal 5 to make this guy 0, or I could have an x equal 3 to make this guy 0. So those are my two solutions for x. X is either 5 or it is 3. Any questions on this? This is pretty important. Don't fall into the trap of trying to, when you see a square term, an x term, and a constant, of trying to get all the x's on one side. Just get everything on one side and factor. And this will only work if you have a 0 on this side. You have to have 0 over here. If you have 15 over there, it's not going to work. It has to be 0 over there. Okay, cool. We're not going to do that one. This guy we can do. Make sure that this is correct, as it is. 1 second. Yeah, we are good on that one. Good. Okay, cool. So with this guy, it's a little intimidating because we've got variables in the fraction, or variables in the denominator, fractions and stuff. That's fine. Just remember the first step is multiply to get fractions out of the denominator. Okay, so I'm going to give you 1.5 minutes on this guy, and you can do some rearranging. All right, so your time starts now. Okay, cool. We're starting to get some answers in here. Okay. Without getting too far into the weeds, we want to multiply or cross multiply to get the variables out of the denominator. So the first thing I'm going to do is get that z out of there. Okay. So get that z out. You're going to multiply by z and by 2z. So cross multiply. Z up here, I get z times 3z minus 6 is equal to, and then I cross multiply here, 2 minus z. If I multiply through here, I get 3z squared minus 6z is equal to 2 minus z. I notice that I've got a square term and linear term and a constant, so now I'm thinking I'm probably going to be doing a factor problem, okay? But let me combine like terms. So I'm going to get everything over to this side. 3z squared minus 6z is going to stay. Now I'm going to add a z over here and add one over here. And I'm going to subtract the 2 from both sides too, okay? So I just got everything from this side over here now. Okay, so I combine my terms. I get 3z squared minus 6z plus z is minus 5z minus 2 is equal to 0. Is that right? Have I multiplied that through correctly? I think so. That looks okay. Yeah, I think that looks good. Okay, cool. So now I just need to factor this guy. And unfortunately, it's not the easy kind. It's the kind where I have a coefficient. Okay, so I'm going to look at my factors of 2. And luckily, 2 only has one set of factors. It's going to be 2 and 1. And one's going to be positive and one's going to be negative. I just don't know which is which. But because I'm going for a negative number here, let me try a minus 2 out here to make a negative 6. And a positive 1. So negative 6 plus 1 makes minus 5. So that's going to work for us. Now I have this situation where I've got my 2 sets of parentheses multiplied together equals 0. In order to solve for z, then, I have to assume that either this one is going to make 0. So that would be z is equal to 2. Or this one equals 0. Now, how do I make 3z plus 1 equals 0? Well, that'd be like 3z is equal to minus 1 It would be if z is equal to -1/3. That would make 0. Okay? Because z times, so that would make a -1 plus, yeah. So my two solutions here are that z is either equal to -1/3 or it's equal to 2. Okay? And here's the last thing, okay? Because we've got, okay, so we've got two possible solutions here. Okay, so quantity A is greater. No, it's either equal or the same. So it's definitely not A. Quantity B is greater. Well, we don't know. It could be the same or it could be 2. So that's not right. But the other thing is that we've got this 2. If we had 2 as a solution and we plugged it in here, if we had a 2 up here, that would give us a 0 in the denominator. Okay, and that's not allowable. We cannot have a 0 in the denominator. So this is not actually a solution. Okay, can't be solved. When you have a 0 in the denominator, it can't be solved. So that is not a solution. So that means the only solution we have is that z is equal to 1/3. And so for that reason, or -1/3, and so for that reason, the two quantities are equal. Okay, so we cross multiplied. We combined all our terms and got them over to one side, and then we factored. And then the last trick in this problem, yes, tricky, exactly, is that you get your two solutions, but then you can't use 2 as a solution because of the 0 in the denominator. And that's something, a very GRE tricky thing to watch for. No zeros in the denominator, because they do like to get you on that, okay? That is very tricky, but a common trick, right? Okay, so from there, these modern math problems, the ones where they give you a symbol, one of the first problems in this course is the C minus C dot problem. This is the similar idea. They should not be intimidating problems. These are great ones to do. The word problems, like I said, those you can waste a lot of time on and never really get any better at them. The modern math ones, they are well worth your time because they're frequently very easy, just like cut and paste problems almost. But they look threatening because they have weird symbols in them. What they will do is they will give you symbols like an A inside square brackets, and then they will tell you what that means. And all they're saying then is if they give you A in a bracket is equal to 1/A minus 3A, all you're going to do is take whatever A is in that bracket and put it into this formula. Okay, so for example, if we had 5 in brackets, the problem tells us all we do is that becomes 1/A5 minus 3 times a 5. We just plug that 5 in anywhere A is. Okay, in other words, it's a function problem. Okay, so don't be intimidated because that's a whole lot easier than writing a word problem. Okay, and they're mostly like this. So here we have the example of this. This one didn't turn out that well. Let's see. Let's just make it this. Let's just say A triangle B is equal to A times A plus B. Okay, so let's say they're giving us the definition of A triangle B is the same thing as A times A plus B. Then they might ask you, what is the value of 2 triangle 3? So what would be the value of 2 triangle 3? All you need to do is plug in 2 for all the A values and 3 for all the B values. Yep, Nike, that looks good. So 2 triangle 3 is going to be equal to, we're going to put a 2 in for all these spots. We're going to put a 3 in for all the B spots. So 2 triangle 3 is equal to 2 times 2 plus 3, which is equal to 10. So just put the number in every place that the letter was. All right, so this one, should be, I think. No, I think this should be YZ plus Z. Okay, so X bar Y bar Z is equal to X squared plus YZ plus Z. If N bar 6 bar 9 is equal to 0, what is N? Take a minute on this one. Okay, so this one is a little bit strange, but let me take this here for a second. So if X bar Y bar Z is equal to X squared plus YZ plus Z, I'm just going to plug in here. N bar 6 bar 9 would be, I'll plug in N anywhere the X was, so it's just here. I'll plug in 6 anywhere the Y was. That's just one place. I'll plug in Z, or 9 anywhere the Z was, so that's here. And also the last one. Let me make some space here. Okay, so just plugged in there where they went, and they're also telling us it's equal to 0. All right, so they tell us it's equal to 0, so then I just add a bunch of stuff up. So N squared plus 6 times 9 is 54 plus 9, so N squared plus 63 is equal to 0. N squared is equal to negative 63. Yeah, I knew there was a problem here. Yeah, this should actually be, maybe this should be xy plus z. Maybe they did finally fix it. Anyway, so you end up with the root of negative 63, which is not actually an answer you would get on the GRE, but you do end up with that. Okay. Yeah, so Nike, you had the right idea there. Yep. Okay, I don't want to dwell on that one because I think, again, I think that's an error that we've been sort of stalling to correct. This is a really challenging function problem. If somebody would like to do a really challenging function problem, here's one to work on. It's not challenging, it's a back solving problem. It's just, it's threatening and time consuming. But this is in here if you are feeling confident about function problems. And then we move on to coordinates. And so coordinates are a lot more useful and a lot more common. The way coordinates work, we have X and Y coordinates. X goes left, right, Y goes up, down. Coordinates are given X, Y, meaning they're first you go left or right, then you go up or down. Okay. The little marks along here are called tick marks. They typically are a scale of 1, but they can be a scale of something else. We also have quadrants. The quadrants refer to where you are with respect to the X and Y axes, and they make a C. Quadrant 1, quadrant 2, quadrant 3, quadrant 4. Cool. So this should be Y is equal to S over absolute value of x. I don't know why I just drew that line really long. Okay. I don't know why I'm drawing this so terribly. There we go. Okay. Cool. Okay, so this problem. This figure above indicates the quadrant labels for a rectangular coordinate system. Yeah, 1, 2, 3, 4. In which two quadrants does the equation lie if s is less than 0? And your equation is this. This is an s, and it's over the absolute value of x. Okay. Again, this is a picking numbers problem. Okay. So remember, you're going to pick a few different values. Pick Panoff if that is relevant. Pick a positive and negative, a 0 and a fraction if you need to. Okay. And you got a minute and a half. Your time starts now. Okay, cool. So looks like Hima's got an answer. Awesome. Other answers? Anybody, anybody, anybody? Okay, cool. So let's get started on how to do this one. So the first insight is s is less than 0. So I'm just going to pick a value for s that's less than 0. Okay. So let's just say x is equal to -1. All right. Now, though, I have to try some different combinations for this equation. So I'm just going to pretend that my equation is not s over absolute value, but it's actually just -1. Because the way it's written, it makes it sound like no matter what s, as long as s is less than 0, you get the same results. Okay. Cool. So now this is the equation I'm talking about. Now, once again, with a picking numbers problem, I'm going to be really neat. I'm going to be nice and neat with my table. Okay. And give myself plenty of space to work out my answers so I don't make a mistake. So I'm going to pick, first off, I'm going to pick a positive value for x. If I get a positive value for x, that gives me y is equal to -1 over 1. Sorry, can you see writing now? Great, okay, cool. Yeah, so I just made a table here, x, and I wrote my equation, and I'm going to find y. So I'm going to pick values for x and see what y turns out to be. And I started with 1 because we want to pick positive, negative, 0, fraction, okay? So with a positive value of 1, I put that in, and it turns out the y is going to give me -1. Now, if I put a -1 in for x, then I get y is equal to -1 over the absolute value of -1, which would be 1. And so y is still -1. And I don't need to try a fraction because it won't change anything. And I don't need to try 0 because then I have a 0 in the denominator and that's undefined. So I'm just going to stick with these two, okay? And furthermore, if you were tempted to try a fraction, we'll already have 2 different quadrants by the time I do these two, and so we don't need to try more. But anyway, so depending on my value for x, I either end up with a 1, -1 down in this quadrant, or a -1, -1 down in this quadrant. So my answer is going to be a 3 or 4. Okay. Is that one understandable, how I did this one? I think it takes a little bit of confidence to be like, okay, I'm just going to pick a value for s. Okay, and then from there, it's just a matter of being neat and filling in your values for x and y. Okay. Let me just get into some stuff about x and y axes. Positive stuff is up in the right, negative stuff is down and left. Here they just point out that the tick marks don't need to be 1. Here you could see a graph where each little tick mark counts for 2, 2, 4, 6, 8, 10. This is a challenging problem, 160-ish. If you'd like to do this one, it's a cool problem. Then we get to this stuff, identifying slopes by site. Very important to know this. Positive slopes go up. Negative slopes go down, go up to the right. Negative slopes go down to the right. Horizontal slopes are 0, and vertical lines are undefined. They have an undefined slope. And again, that's what happens when you have a 0 in a denominator, and that's why we don't like it. Okay. Cool. If you want to find the slope of a line, we have a couple formulas to do it. This is all out of whack, but the formula is rise over run, otherwise known as change in y over change in x, otherwise known as y2 minus y1 over x2 minus x1. And what do we mean by rise and run on y2 minus y1? You need 2 points to define a line. Okay, so if you had 2 points, if you had like the point 1,5 and the point 0,4, you have 2 points. And if you wanted to find the slope of them, you would take, let's say this is 1 and this is 2. You would take y2 minus y1, so that's 4 minus 5, and x2 minus x1, and that would give you -1 over -1. This line has a slope of 1. That's how you find the slope from 2 points. Lines that are parallel have the same slope. That makes sense, right? If slope is a measure of how steep they are, if they're the same steepness, they're going to be parallel. Perpendicular lines, they're the negative reciprocal. So if our slope of this line up here was a slope of, well, actually that's a bad example, but if so we had a line with a slope of 2, the line perpendicular to it would have a slope of -1 over 2. If you had a line with a slope of 3/4, the perpendicular line would be -4/3. Okay. Okay, so parallel lines have the same slope. Perpendicular lines have negative reciprocal slopes. Cool. The way to find a slope is something that we call slope-intercept form. Y is equal to mx plus b. So if you need to find the slope of something, you transform the equation so that y is alone over here and everything else is on the right side. This here is whatever the coefficient of x is, okay? And that is your slope. So for example, if we had a line y is equal to 5x plus 3, the slope of that would be 5. That would be the slope. The y-intercept would be 3. Now, what does y-intercept mean? What does it sound like? It's where it intercepts or hits the y-axis. In other words, It is the place that it crosses the y-axis. And it can cross it in this direction, or it can cross it in this direction, but it's the point that it crosses the y-axis. That's called the y-intercept. Okay? That is slope-intercept form. For this problem, though, we don't need the intercept. We just need the slope. So with this one, you got 1.5 minutes. You've got to transform the equation into slope-intercept form and find the slope. Your time starts now. Okay, so, oh, sorry, we can scroll back here. There we go. Okay, so in the xy plane, what is the slope of 2x plus 2y equals 7? So we need to transform it to slope-intercept form. We're going to get the y alone. In order to do that, we get the 2y, we have the 2x over on this side. Now we're going to divide by 2. That gives us y is equal to 7/2 minus x. So what is the coefficient of x? It's going to be a -1. So the answer here is B. Okay. Yeah. So good answer, Hannah. Good answer, Lauren. Awesome. Okay. So moving on from there. What happens when we get 2 points and we need to find the whole equation just on those 2 points? Well, we can still do that. We just have to find the slope as well as the intercept. So we can start out just by finding the slope. And like I said, when you find the slope, the first thing that you are going to do is try and find y2 minus y1 is x2 minus x1. So if we call this our first point, and this our second point, y2 minus y1 is equal to x2 minus x1. So y2 is -1 minus y1. Let me just write this. Too many ones here. Okay, cool. All right, so y2 minus y1 is going to be -1 minus 3. x2 minus x1 is going to be 6 minus 5. So that gives us a -4 over 1. So our slope is going to be -4. Cool, so that's our slope. But then we have to find the y-intercept. That's a little bit weirder because now, let's see, if I wanted to write out the slope-intercept, the slope-intercept formula, I would have y is equal to negative 4x plus b. Because I know the slope, but I don't know the intercept. That's 3 different variables in one equation, and that's crap, right? You actually need to have one variable, one equation, okay? So the good news is we have lots of different x's and y's to work with. We can use 5 and 3 and 6 and 1. We can use those to find our intercept, okay? So that's what we're going to do. I'm going to take this 5, 3, and I'm going to plug it in here. So I'm going to put the 3 in where the y is, and the 5 in where the x is. Sorry. Negative 4 times 5. Okay. So I just took my values and I plugged them in. And I could have used the 6 minus 1 point, doesn't matter, but I'm going to use these two. So 3 is equal to minus 20 plus b. b is equal to 23. So now I've identified my slope here, and I've identified my intercept here. So now I can write the equation. Y is equal to negative 4x plus 23. Okay, so that's how you can write an entire equation for a line just based on 2 points. Find the slope. Then you're left with this rather sparse looking equation that has an x, a y, and a b in it. But just take one of your points and fill in the x and y, and that'll help you find your b. Okay. All right, cool. So now we're going to do a little bit of comparing. Again, this here would be the y-intercept because it's where it crosses the y-axis, okay? So this one, unfortunately, you got to do a little comparing with the answer choices, but you got a minute and a half to figure out which of these equations is represented by the picture. And your time starts now. Okay, so what do we have here? There's a little bit of comparison shopping that goes on here. So, which of the following represents line B shown in the figure above? Well, we can look at this and we can find the slope and the intercept, right? We know the y-intercept is going to be negative 1, 2, 3, 4. So our y-intercept is negative 4. Our slope, well, our slope, it's rise over run, or y2 minus y1 is x2 minus x1. So we know that we have one point here that's negative 3, 0, and another point here that's 1, 2, 3, 4, that's 0, negative 4. So if you wanted to find the slope of this line, you could do y2 minus y1 over x2 minus x1. So that would be negative 4 over x2 minus 3. So your slope is negative 4/3. The other thing you could do is sort of count Okay, so you could say, okay, from here, I'm going over 3 and down 4. So my rise is 4 and my run is 3. And because it's down this way, I know it's negative. Okay, so that's, you could just do it visually too. Okay, so now I know that my equation, this is the slope and this is the intercept. I'm looking for an equation ultimately that looks like y minus 4/3 minus 4. Okay, so looking at all these choices, you're going to have to rearrange them, unfortunately, and you can sort of start to get to a sense for which one is going to work out better. Okay. For example, you know that you need to end up with a negative intercept. All right, so just starting in the middle for no particular reason. If I get y alone, 6y is equal to negative 8x minus 24. If I divide by 6, divide by 6, divide by 6, that gets me y is equal to negative 4/3 minus 4. So that's looking really good. Looking good. Okay, let's try another one. If we try d, however, minus 8y. Sorry, if I want to get y alone, I'll bring that over to the other side first. So I would get 6x minus 24 is equal to 8y. If I divided this by 8 and this by 8, this is going to give me a positive slope, so that can't be right. Okay. Similarly with this guy, I think. Yep, with this guy, I'm going to get a positive slope. 8x plus 24 is equal to 6y. So if I divide by 6 all the way across, I'm going to get 4/3 x, not negative 4/3 x, so this one's out. In any case, if you try all of them, you find out that this one, C, does. When you rearrange it, you get exactly what you want. You get minus 4/3 x minus 4. And we determined that's the correct slope and the correct intercept. So the answer is C. Okay. Okay, from there, let us do this guy. Okay, let me rewrite this. This should be x squared minus 6x plus 5 over x plus 2 times x plus 5. That's equal to 0. Okay, got a minute and a half. We'll make this our last problem before we take a break and move on to the next section. Okay, so you got a minute and a half, and your time starts now. Okay, so let's work on this guy. Let's see. So your instinct is hopefully at this point when you see something that is a combination of a square, an x, and a constant to factor. Let's factor that top guy first. So we factor that one. Set up my parentheses. We're going to have an x and an x. And we're looking for factors of 5 that add up to -6. Okay, so -5 and -1 would be the factors over x plus 2 times x plus 5. And we know that that's supposed to equal 0. All right, so we need solutions here. Well, interestingly, there are 2 ways to get a 0. We could have but we need, well, not really actually. So we can't have any values of x down here that will make 0 because we don't want a 0 in the denominator, right? So we know that x does not equal -2 and it does not equal -5. Okay, that's not helpful to us. Okay, up here though, if we want it to equal 0, we have 2 options, right? X can equal 5 or x can equal 1, right? Those are the 2 things that will give us equal to 0. Okay, so if our possibilities are that x is equal to 1 or 5, both those options are bigger than quantity A, so the answer is B. Okay. They try to tempt you down here with the road being like, they try to tempt you down here to think that this is the problem, that if it's -2 or -5, that'll give you 0. That's not true, right? Remember, 0 in the denominator is undefined. It's not an answer. We want 0 in the numerator because 0 in the numerator will give you 0. Okay. Yes, they're very tricky, Hema. They're very tempting and tricky. Cool. All right. So with that, let's take a break. Come back at 50 minutes after the hour, and we will move on to bigger and better things. This was a huge slide. This is a 48 slide deck, just so you know. It's huge. Okay. Okay. So I'll see you in just a few minutes, and we will go on to do some data interpretation stuff, which would be fun. 5 minutes. So come back 50 minutes. Oops, sorry, I just typed that into organizers after the hour. So 50 minutes after the hour. Okay, cool. See you in a bit. All right, cool. So let us get started back with some stuff that's a little different, a little more fun maybe, I don't know. Data interpretation. So the GRE does ask you at the end of the quant section, there's always several questions devoted to data interpretation. They can be time consuming. It's good that they're at the end because they can take up more time sometimes than other questions, and they're not worth any more points. So it would be bad if they were at the beginning because people might be lured into spending too much time on them. But that being said, if you're good at reading graphs, this is a good place to pick up points. You'll usually get about 6 of them at the end of the quant section. So it's all about graphs. There's charts, there's graphs, there's tables. We don't really care the difference between a chart and a graph. A bar or line graph is something that looks like this. It's just really important when you read a graph, read the title very carefully and read the axes very carefully. You also want to be real concerned about what are your units, okay? Okay, are we in inches? Are we in percent? What are we in, okay? So that's title and then your axes. Be very, very clear on those, okay? So if we wanted to interpret what this graph is about, we would say, oh, well, it's about the total rainfall in inches over 4 months. And the title, there's no title here, but maybe it's for, looks like it's a place that it rains quite a lot in May. Looks like a monsoon climate, actually. Okay. So anyway, so this is the most important thing about it is just to be clear on what the graph can tell you. Okay. Here you'll see in our first practice problem, we've got a percent. Okay. One of the ways they love to mess you up is by using a percent when you're expecting it to be a number of students, or using a number of students when you're expecting it to be a percent, that kind of thing, okay? So in this question, I'm going to release you onto it, but just be clear about the fact this is a percent over here, not a number of students, okay? So take a minute and a half, and your time starts now. Okay, looks like we're getting some answers in. Cool. All right, so rolling on here. The graph is showing us a percentage of students. So what they've done is they've given us the easy task on the 100 sixth graders and 100 eighth graders. So that's easy because the number of students is the same as the percent of students. The more difficult one is the 7th graders. They're 150, so we're just going to have to deal with that when we get there. Okay, we look at our title, language class elective, and then the scale shows us that the key shows us that the dark gray is the French. So we want to be looking at the dark gray bar. So it looks like about 25 to about 82 here is French. So that's like what is that? Yeah, like 25 to 82 or something like that. Yeah, so that's like 57 people, something like that. So there's about 57 kids there. In the 8th grade, it looks like we got from about 10% to about 32%. So that's about 22 kids. Okay, so far in the 6th grade, we got about 57 kids. In the 8th grade, we got about 22 kids. And then the 7th grade, we've got somewhere between the 75th percent and the 32 or so. So there's about 53% of the class is taking French. But because we're dealing with 150 kids, not 100 kids, we need to multiply, right? We need 53% of 150. So how do we do 53% of 150? Well, you can do 0.53 times 150. You can also take 53 and then add half that again. But because you got a calculator, you do 0.3 times 150. You get 79.5, so let's say it's 80 kids. Okay. So if we add them all up, did I way overestimate here? 10 to 32. It's about 22. Did I do this 25 to, I feel like this bar didn't used to be quite this long. 25 to 82. I'm sure that this graphic has translated the way that it used to. Anyway, so we add them up, get 137 plus 22. That gives you 159. That seems a bit high, right? I feel like this bar might be a little bit estimated. Anyway, so Ashmini and Lauren, you got E and D. Okay. So how did you do it? Did you do the same thing where you measured the space between these two bars? I just feel like this bar used to end here, okay? And bar here. And then this one, you take whatever this percentile is times 150. Okay. Cool, yeah. All right, so whatever you got, that's right. I think there might be a mistake in this graphic now. It used to be that it was pretty close between 130 and 143, probably even closer than on the test. On the test, it shouldn't be that hard to eyeball. You gotta be a little careful, but not super careful, okay? So in any case, if you got D, that actually was the answer. Some people answered C because I think you ended up with about like 137 or something when you added them up. Yeah, so anyway, so if you got D, that's the right thing. And Ashmini, if you add this and then multiply this times 150, whatever you get, that's should be around 143. Do you see where I'm going wrong here? 30 to 40. Oh, I'm sorry. This is 30. So this should be 43%, right? This should be 43%. So if we do 43% of 150, that gives us 65 kids. Does that get us closer? If this is 65. So now we have 57 and 65 and 22. Yeah, that gives me 144. Yeah, so 143 is the estimate. Yeah, I'm sorry. So that was my bad. That this should be 43%, not 53%. Okay, cool. All right, cool. So that's a bar graph problem. Now we get to a line graph, kind of a similar idea here. Okay, the graph above shows a daily range of temperatures for 2 cities. What is the range for daily maximum temperatures in city A? Just to be clear, range means the biggest minus the least. Okay, so take a minute on this one. Okay, so from here, the graph above shows the daily range of temperatures for two cities over a 1 week period, with city A above city B. So city A is dark, city B is light. What is this daily range of maximum temperatures for city A? Okay, so we only need to pay attention to the dark lines here. We're only interested in city A. We want the range for daily maximum temperatures. This is giving us the temperature range for the day. We want the maximum temperatures. So this would be the max, and this is the max, and this, and this, and this, and this, and this. So if we want the range of maximums, we want the greatest maximum minus the least maximum. I think that's right. So that would be, this one looks like it's about 2, 4, 6, 8. This one looks to be about 89 degrees or so. And this one looks to be about 81 degrees. So what is the range between them? 8 degrees. The answer is B. Okay. Okay, so here's another problem involving range. Okay. This also gets at the idea of median. So we've got mean, median, and mode. Mean is average. What's the median of something? What is the median? The median is what you get. Yeah, it's the middle number. When you line them up in ascending order, the number that's in the middle. So if we have 5 values, we line them up in ascending order. The one in the middle is the median. If you got 2, if it's like even number of things, then you take the average of the 2 that are in the middle. Okay, so the middle number. All right, cool. So you need that to solve this problem. It says the table above gives the information about the current price range of dollars of 167 items in the store. If M is the median price, which of the following must be true? And then it tries to tell you, so where is the median? Is it in this box? Is it less than $5? Is the median between $25 and $34? Where's the median price? Okay, so take a minute on this one and see what you come up with. Okay, so we're getting some answers on this one. The key here with the median problem is to make sure that you are accounting, make sure that you are doing your accounting properly. So with this guy, we have 167 items in the store, right? So we got 167 items. That means there are going to be 83 items down here and 83 items up here. And then your middle item is going to be that 167th item, right? Okay, so we need to go through we need to go through 83 items before we get to the median price. 4 of them are less than $5. The next 27 are in this box, so that gets us up to 31 items. The next 39 are in this box. That gets us up to 70 items. The next 13 are in this. That gets us up to 83 items. And so now we're here. The M then has to be in the next box. The M has to be in this box, 35 to 44. So the answer is E. And then all the higher priced items are up here. It'll be the next 46 of these, and then 28 of these, and then 9 of these. Okay. So the answer to this one is E. Okay. So let me get into pie charts. Pie charts are usually used with percents. Sometimes they do combine them with geometry problems. And so they'll say, what angle is this 5%? Okay. If they do that, that's okay. We can handle that. If there are 360 degrees in a circle, and we'll be doing more geometry. We haven't done geometry, that's for next time, but they're 360 degrees in a circle. So if we want to know what angle 5% is, we just do that. We take 5% of 360. Right? Just like it won't surprise you that if we take 25% of 360, it gives us 90, right? A quarter of the circle is a 90-degree angle. Okay? So that's how we go back and forth. That's just a kind of somewhat common in these pie chart questions, is to kind of combine them with a geometry problem. So you have to take a percent of 360, okay? With that said, here's the next example. Here they're asking you the degree measure of the central angle of the sector, blah, blah, blah. What that really means is they're saying what degrees is the wedge, okay? So in the circle graphs, the degree measure of the central angle of the sector representing the number of employees who use 6 to 8 sick days. Okay, so we're talking about this wedge here is how much greater than in the company B graph than the company A graph. So we're comparing these two sectors, but they want to know what's the difference between this angle and this angle. So we would take 15% of 360 over here and 20% of 360 over here. Or another way to do it is just say that the difference between them is 5% of 360. So 5%, the difference is 5% of 360 because we got 15% on one side, 20 on the other. And that gives you 18 degrees. So the answer to this guy is 18. Okay, so that's something to be just watching out for those pie chart problems, is frequently they'll do an angle combination thing. Okay. All right, cool. So then we get to this type of thing. Here we've got a little bit of a range problem, a little bit like that 167 items problem, but there's a sufficiency element to it. So what these are saying is they will give you some information, but it will not be a complete amount of information to answer the question. They will then give you, in the answer choices, they'll give you a couple of additional pieces of information, and you're supposed to say, okay, is this enough for me to answer the question? So here they're telling us that we have a range of book prices at Cup and Chaucer. It's $80. And the range of prices at Book Nook is $75. So we've got these two bookstores, Cup and Chaucer and Book Nook. Cup and Chaucer has a range of $80 between their most expensive book and their least expensive book. Book Nook has a little smaller range. It's $75. What we don't know is we don't know if they're at the high end or at the low end of prices. Okay, they could be way more expensive than any book at Cup and Chaucer, or they could be way less expensive than any book at Cup and Chaucer. Okay, we don't know the range. Okay, so what they're asking us is which of the following statements provides additional information to determine the range of book prices for all books at both bookstores. Right now, we can't tell because we don't know if their prices overlap at all. If they overlap completely, then the range is $80. If they don't overlap at all, you can have a huge range from like $1 up to $1 million. Okay, so we're going to need some more information. And your job with these statements is to reason Which one gives you enough information to know the range of the books? Okay, is the question clear? Do you understand what they're asking? They're basically saying, how much do these things overlap? Okay, so let's reason through these together then. All right, so we know that Cup and Chaucer has some expensive books, maybe some cheap books, I don't know, but there's an $80 difference between the most expensive and the least expensive book. Same with Book Nook. There's a $75 difference between the most expensive and the least expensive book. If we want to know the range of book prices for all books, what we want to know is the cheapest book up to the most expensive book combined. So we don't know if it's like this or let's see, can I move these all together? Or like this, you know, or maybe Book Nook has only really high-end books, or it could be like this, where they half overlap or something like that, in which case they might have a range of like $80 and then an extra 30, something like that. Okay, so we just don't know the range of both books combined. So with statement A, they give us more information though. The median book price at Cup and Chaucer is $5 greater than the median book price at Book Nook. Oh, I'm sorry. So something else we could say is, what would be sufficient to answer this? So in order to know what the full range of books is, then what pieces of information do we need? Well, I would say we need the most expensive book and the least expensive book total, right? That would be sufficient for us to know. We need most expensive book and least expensive book in both stores. So first one, the median book price at Cup and Chaucer is $5 greater than the median book price at Book Nook. Okay, well that's fine. We can imagine adjusting the median here. So Cup and Chaucer is a little bit greater. We can shift this up a little bit, for example. But the thing is, we don't know if they have a whole bunch of books that are $81 or if the upper end of their books spread out to $10,000. We just don't know. So that one can't be sufficient. Okay, so then we get to the most expensive book at Cup and Chaucer is $15 greater than the most expensive book at Book Nook. Well, that's useful to know, right? That means that this one is $15 and this one, so if this one is, we know that this space here is $15. And that does help us figure out our range, right? Because if we know there's a $15 gap between the two of them, then there's another 60, then the 75 extends all the way down here. Okay, so this actually would be enough range to tell us. Because they're not fully overlapping, they're $15 offset from each other. So the 75 would actually stick out $10 more down here. Okay, so that one probably is enough. We look at C. The average book price at Cup and Chaucer is $4 greater than the average book price at Book Nook. Okay, now again, average isn't going to help us because what we really need is something having to do with the most expensive book price and the least expensive book price. The average doesn't tell us anything about the endpoints. Okay, so C cannot be sufficient. So the answer here has got to be B. Anyway, so this is a sufficiency question, and you can expect to see just a couple of these on the test. They're pretty unusual. But the idea here is that you are looking for what is sufficient information. They're logically more difficult, but they're easier in the sense that you don't actually have to ever solve the problem. Like here, I don't actually have to figure out what the range is. I just need to know that this would be enough information to find it. So that's the good thing about them. So those are sufficiency questions. Okay. Let's do this guy. Okay, here's a different kind of sufficiency, and it kind of uses some of our algebra stuff from the last deck. So here they're saying if x plus 3y equals 9, then which of the following statements provides sufficient and additional information to determine the value of x? Okay, remember, we got two variables, so we can't solve for x right now, but we want to know which of these gives us enough information that we can solve for x. Okay, so take a minute on this one, and your time starts now. Okay, so with this one, let's see. You would expect that you would have a second equation ought to be enough, right? If you have a second equation, you can solve for the missing variable. There are a few situations where you can't, and this is worth paying attention to. The situations where you will not get a solution are the following. If you end up rearranging these equations and they turn out to be the same equation, okay? So, for example, x plus 3y equals 9. If you multiply some of these through, like this one might do it. I think it's the other way around. If you rearrange it in this, and it turns out to also be x plus 3y equals 9, one of these things, then you don't have two different equations. So that will not provide a solution. The other time you won't get a solution is if it turns out these are the graphs of lines, remember? And if it turns out the lines never cross, if they're parallel, if they have the same slope, there will never be a solution. Because the definition of a solution to a system of equations is where the lines cross. If they're parallel, they never cross, there's no solution. How do you know? They'll have the same slope. Okay, so we are looking for an answer here that it can't rearrange to make the same equation as provided, can't have same slope, which as equation provided. Those are our two criteria. Okay, so we go through our options here, and it turns out that this one, if we rearrange it, we get y is equal to negative 3x plus 9. This one, if we put it in slope-intercept form, we get 3y is equal to 9 minus x, divide by 3, divide by 3, divide by 3. So y is equal to 3 minus 1/3 x. Okay. So do these give us the same slope? No. So this one looks to be okay, right? It's not the same equation. It doesn't have the same slope, so we're all right. So we move on to B. This one is not the same equation, but it does have the same slope. It's still a negative 1/3 x. So that one is not right. This one here, if we rearrange it, we get 9y is equal to negative 3x, divide by 9, divide by 9, y is equal to, negative 1/3 x. Again, this will have the same slope, so that can't be right. This one here, we take 3y is equal to x minus 1. Y is equal to x over 3 minus 1/3. This is a positive 1/3 x, so that's okay. We can live with this one. So far we've got A and we've got D as our answers. Then we look at E as our last one, x minus 1/3 y plus 3. Okay, well, we want to, remember, don't get the x and the y confused. We want to get the y alone. So if we do that, we get 1/3 y is equal to negative x plus 3. Multiply both sides by 3, we get y is equal to negative 3x plus 9. And we're okay with that one. That one's okay too. So the answers here are A, D, and E. Okay. But that's just to alert you to the fact the way that you get two equations, when you have two equations, two variables, but no solution, it's if they're actually the same equation, or if they have the same slope, it means they'll never cross and there can't be a solution. There is no solution. Okay, so that is it for data interpretation. Let's take just a real quick break so that I can refill my teacup and you can go to the bathroom if you want. And we will come back at 27 minutes after the hour to finish up with some stuff about averages and sets. Okay, standard deviation, that kind of stuff. Okay, statistics problems. Cool. So I will see you back here at 27 minutes after. Okay, cool. So let us finish up with, oh, we're way ahead in this sec. Some stuff about statistics on the test. Okay. So are we showing this? Yes, great. We already did a couple problems in the last deck that involved this, but averages are the sum of terms divided by the number of terms. Okay. If you have, you know, if you get an 80, and 100 on a test, plus 80 plus 100, on 3 tests, you do 260 over 3. Okay. And your average is something like a, what, like an 80, an 87 or something like that. Okay. Cool. So that's the average. The mean, the median, the mode. So the mean is, that's the average. So 1, 2, 7, 7, and 8, you would add them up and divide by 5. You get 5. The median in this set, we would line them up in order, and the middle number is a 7. The mode is the most common number. That's also 7. And the range is the difference between the greatest and the least, and that's also 7. Okay, so pretty straightforward. The standard deviation is not something you have to calculate on this test. The only thing you need to know about standard deviation is it measures how spread out your data are. Okay, a small standard deviation means close to the mean. A high standard deviation means spread out from the mean. Okay, so you figure out what your average or your mean is, and then you decide, are my data points really close to that or really far from that? And if you want to think about it graphically, you think about the bell curve, right? If this is the mean of the bell curve, okay, something with a small standard deviation would have most of its values right next to the mean like this. This would be a low standard deviation, or small. Okay, something with a large standard deviation would have the data like really spread out like this from the mean. Okay, this would have a large standard deviation. Cool. So in this example, it says which set has a greater standard deviation? 1, 2, 7, 7, 8, or 4, 5, 5, 6, 7? Which one is a greater standard deviation? Well, the first step is you find the mean, which in this case, because I've done it before, is 5. And in this case, the mean is, I forget, it's like 4.5, I think. 4 plus 5 plus 5 plus 6 plus 7 divided by 5. Yes, 5.4. Sorry, I had it the other way. Okay, so your mean is 5, and here the mean is 5.4. So then you say to yourself, okay, which one has the values, the greater standard deviation? So which one has values that are further spread out from the mean? Well, here we're like, the 1 is about 4 away, and the 8 is 3 away. So that's pretty spread out. Up here, the 4 is only 1.4 away from the mean, and this is only 1.6 away from the mean. So yeah, this one, it's more spread out. This one has the greater standard deviation. Okay, so find the mean and then decide how far away the endpoints are. And it's actually not just the endpoints. If you have a big set of data, it's kind of the aggregate. You know, if you had every value really, really close to the mean, and then you just had 2 endpoints out here, that still might have a small standard deviation. It's kind of your general sense of how spread out everything is. Okay, but again, you don't need to calculate it. You just need to know that it measures how spread out data is. Okay, so here's kind of an interesting problem. A set of 17 different integers has a median of 44 and a range of 45. What is the greatest possible integer that could be in this set? So I'll give you a minute to think about this one, and your time starts now. Okay, so that's a minute. We've got the set of 17 integers. It has a median of 44 and a range of 45. Okay, so 17 integers. That means we've got 8 below, 8 above. And then this is going to be our median. So this is 44. It's telling us we got, excuse me, different integers. So if we got 8 integers below 44, and they have to be different, that means that we have to start at like 36, right? 36, 37, 38, 39, 40, 41, 42, 43. That would give us 8 different ones. So we have to start at 36. We can't start any higher than that, or we're going to have overlap before we get to 44. So you got to start there. And we don't want to start lower because ultimately we're looking for the greatest possible integer that could be in the set. So if we start having lower integers, then we're going to have to shift our whole range down. Okay, so if we start at 36, that's the highest we can start at. Then we add 45 to that, right? Because the range is the difference between the highest value and the lowest value. So we add 45 more to that, we get up to 81. Yep, so if we have a range from 36 to 81, it's a range of 45. So the answer here is C. Okay, so that's a good median problem. Don't need to do this guy. These graphs you see, you might see these in data interpretation. It's a histogram, basically, but it's a frequency. And what it's showing you is basically what percent of times you're going to get a gummy bear out of a bag. So a bag of gummy bears is like 17% yellow, 20% red, 22% green. Yuck. 17% white. Those are my favorites. 15% orange. Okay. But this is just a frequency diagram that you might see. We're more used to seeing them look like smooth curves. That's exactly the same thing. A bell curve is a frequency diagram. It's just it's done as a big line rather than individual bars. Yeah, here's a probability distribution, same deal. You know, this is just showing that the likelihood that you are going to, you know, the percent of coin flips in 10, like you're going to get 25% of the time, you're going to get 5 heads in 10 coin flips. So same idea. All right, let us do this guy. The table above shows the frequency distribution for the heights of students in a certain class. If a student is selected at random from the class, what's the probability that his or her height is between 61 and 67 inches inclusive? Okay, so for those of you who are there this weekend, you can remember that probability is desired outcomes over total outcomes. Okay, so what we're concerned with here is how many total students are there, and then how many of those are within the desired range. Okay, so take a minute with this one and see what you come up with. All right, so let us see. We got desired over total. Here we go. Cool. So the total number, if the student selected at random per class, what's the probability that his or her height is between 61 and 67 inches? Okay, well, we've got 1, 3. How many students we have? We have 1, 3, that's 4, 6, 11, 13, 14, 15. So we got 15 students. Okay. How many of them are between 61 and 67 inches inclusive? Okay, well, we know the 63s count, the 64s count, and the 66s count. So we want to do 3 and 2, so that's 10 of the students. So total at 10 out of 15. It's a total of 2 out of 3. So our odds are 2 out of 3 that we'll get a student that lies within that range. Okay, so moving on from there. We get to these box and whisker plots. Box and whisker plots are, you'll sometimes see these. They're trying to give you a little bit more information than just a range would or just an average would. These are also relevant when you're applying to programs. They might tell you what the 25th percentile and 75th percentile GRE scores are. And that gives you a little bit more information than just the mean, right? Because the mean can be really, really swayed by a few different values. 25th and 75th percentile kind of give you a little bit more of a sense, like, are most of the people over that mean? Or most of the people under that mean? We don't know. So the way it works is this. The whiskers on the plot, these lines that go out the side, show the full range from the very lowest scores to the very highest. The median is the median. This box represents the 25th percentile and the 75th percentile scores. So you can see here, if these were a number of days employees biked to work in September, there was everything from 1 day to 22 days that people biked. The median was about 9, and it looks like more people biked more than 9 than less than 9. Okay, that this was it was a little more popular than 9 days. If you had to guess, if you met somebody, you would guess that they biked more than 9 days, maybe. All right, cool. So, let us take a look. I'm trying to see. Let's do this problem here. So here we've got the median home price in City A is $15,000 higher than the median home price in City B. Quantitative comparison. And just to be clear about 20 percentiles, I'm pretty sure you guys know this, but a percentile is how many houses were cheaper, how many people did worse. So this here would be the 25th percentile. That means that 75% of people bike to work more than that. 25% of people bike less than that. Okay, so in this case, the home prices, the 25th percentile of home prices in City A means that 25% of houses are cheaper than that. Okay, all right, so take a minute on this one, and your time starts now. Okay, cool. So we get an answer here. The median home price in City A is $15,000 higher than the median home price in City B. Okay, so with this one, yeah. So Lauren, you're saying D? And that's right, right? Because if we can imagine a box and whisker plot for this, just kind of arbitrarily, let's say we have City A and City B, and we get our box and whisker plots. Okay, the median in City A, let's say, is 25,000. And the median in City B is 10,000. Of course, these are very cheap houses. okay? We don't know anything about the range, right? We don't know if this goes down to 0 or if this goes down to $24,000, right? We know nothing about the range here, so we can't possibly know anything about the 25th percentile. So in this case, the relationship cannot be determined. Good answer. Okay. Cool. All right, so then we get to this stuff about, should we do this one? This is a pretty good problem. I'm going to skip it just in the interest of time. This is a 160-ish kind of. This is a good problem, though. That's one's worth doing, okay? But to get onto these Venn diagram problems, sets can be represented with a Venn diagram. So you've probably seen how problems like this, and I want to show you one of these for sure. Frequently they'll have to do with like the students that are in the band or playing an orchestra, students who take French and Spanish classes, and some take both and some take neither, that kind of stuff. Here we've got a development of 80 homes. Some have a garage, some have a pool, 35 have both. How many homes have neither? So this is what we would call a Venn diagram problem. If you've seen Venn diagrams, they're the ones that involve these circles like this, okay? Hopefully yours will only involve 2. They typically only involve 2 circles, although they can involve more. Okay, and your circles are going to represent the fact that we have homes, some of which fall into this group and some of which fall into this group, and some of them overlap. Some are in both groups. Some students take French, some take Spanish, some take both. And then we also have to consider that there's the one on the outside that take neither. Okay, so we also have this box out here. So we have a development of 80 homes. I'm going to call this the garage and this the pool. We know that there are 50 homes that have a garage and 40 that have a pool. There are also 35 that have both. Now the thing is, we can't just add them up and get to 80, right? So how many homes have neither? Well, if we just add these up, 50 and 35 and 40, we get 125, which is like more homes than we started with, and that's all weird. So the formula to know for these problems is it's going to be circle 1 plus circle 2 minus both plus neither equals total. Okay. So, and you plug in according to what you know. So in this case, circle 1 is 50. 50 houses have a garage. Circle 2 is 40 houses have a pool. You subtract out the both. We're wondering what the neither is. We don't know that. And the total is 80. So I add these up. I get 90 minus 35. So that gives me 55. So 55 plus something is equal to 80 houses. So there are 25 houses that have neither. And that's how you solve a Venn diagram problem. When you see these ones about orchestra and band and French and Spanish and this kind of stuff, this is it. And the key here is don't double dip. And these can get really hard, but they aren't always really hard. At this type of problem, just not counting twice, not counting the middle houses twice, it will get you a long way. Okay, so that's a Venn problem. And finally, this is our last topic for tonight, thank goodness, we get to this stuff about probability. And like I said before, probability is desired outcomes over possible outcomes. We talked about this a bit on Saturday. Desired outcomes are the things that you want to happen. Possible outcomes is all the things that could happen. So for example, what is the probability of rolling a number higher than 4 on a 6-sided die? Well, the number of possible outcomes is 6. There's 6 different things you can roll. The probability of rolling something higher than 4, well, that's either a 5 or a 6. So there's 2 possibilities. So what's the probability of rolling one of them? 2 of 6 or 1 in 3. That's the probability. You can also think about the probability of something not happening. What is the probability of not rolling above a 4 on a die? Well, there's a couple ways you can do it. Of course, you could just say a 1, a 2, a 3, or a 4 would all be acceptable outcomes. So if we have 6 total and 4 desired, that means we've got 2 out of 3 is your probability of not rolling above a 4 on a die. Now, the other way to think of it is the probability is 1 minus the probability that it will happen. So what's the probability of not rolling above a 4 on a die? It's 1 minus the probability that you do roll above a 4. And we solved that on the last page. Okay. Our probability that we're going to roll above a 4 was 1/3. So the probability we won't do it is 1 minus 1/3, which also gives you 2/3. Okay, so these match. So you can do it either way. And there's different problems where, you know, one works better than the other. So at the very basic level, that's what a probability problem is. It's desired outcomes over total outcomes. Okay, what happens when we need a few things to happen? Like we need something to happen and then something else to happen. Well, usually we multiply. And the reason we do that is because if you get very demanding and you need this to happen and then this to happen and then this to happen, your odds of getting everything you want get smaller and smaller and smaller. So that means we're going to multiply our fractions. So what's the probability of flipping 2 coins and both landing heads up? I ask you, what is the probability of flipping 2 coins and both of them will land heads up? Well, we need both things to happen. So we are going to flip our first coin, and the odds that it lands heads up is 1 out of 2, right? But then we need the second coin to do that as well. So we're going to multiply and say, okay, multiply, and the odds of that second one happening is also 1 out of 2. Multiply them together, we get 1 out of 4. That's the probability of one coin landing heads up, and then the next coin landing heads up, and you getting both those things happening is 1 out of 4. Okay. The other distinction that we need to make, in addition to just adding one event to another event to another event to another event, and the fractions getting smaller and smaller and smaller, is this idea of dependency. And dependency means basically, does the fraction change every time? Rolling dice is independent, right? Because when you roll a 4, the next time you're just as likely to roll a 4, and the next time you're just as likely to roll a 4, nothing changes. I think of those as dice problems. There are also dependent problems, and these are more like card problems. And in these problems, the fraction changes because as you pull a card out, the deck changes, and then the odds of like getting another ace have changed, right? So if you pull an ace out of a deck of cards, the next time, if you don't put that card back, your likelihood of pulling an ace has gotten smaller, right? You had a 4 out of 52 chance, and now you just have a 3 out of 51 chance. Cool. So what are the chances of drawing 2 aces in a row from a deck of cards? Well, same deal. Our chances in the first pull are 4 out of 52. But then our second pull, there's only 3 aces left, and there's 51 cards left. So if we want to know the probability of pulling an ace and then another ace, we have to multiply across like this. Okay, and this is a dependent probability problem, meaning that this fraction is different than the first one because you changed the state somehow. Okay, and you can do this with cards. You can do this with groups of people. What are the odds of picking 2 girls out of a group of 5 girls and 7 boys? You pull the first girl, and then the odds have changed. The next girl is going to be, a little bit less likely. Okay, and then we get to the or statements. When you need one thing to happen and then another thing and then another thing, your fraction gets smaller and smaller and smaller because you're being very demanding. If you're willing to take something or something else, you're being more flexible. And so the odds of getting what you want get higher. That means we're going to add the fractions, okay? Because when you add fractions, they get bigger. When you multiply them, they get smaller. So when drawing a card from a full deck, what is the probability of drawing either a club or a diamond? Well, we're going to consider the probability of a club. That's 1 in 4, right? The probability of a diamond, that's also 1 in 4. The probability of getting either of those is going to be 1/4 plus 1/4, which is 1/2. And that makes sense, right? Because what's the probability of drawing either a club or a diamond? Well, they make up half the deck. So your chance is 1 out of 2. And then finally, we get to the case where things overlap a little bit. And when I say that, I mean something like this. Here we're going to draw cards from a full deck. What's the probability of drawing either a spade or a queen? Well, the probability of a spade, that's a spade, is 1 in 4, or 4 out of 52. The probability of queen is also, sorry, not 4 out of 52. I'm sorry, that's not the odds there. It's 13 out of 52, a quarter of the deck. The probability of drawing a queen is 4 out of 52 because there are 4 queens in the deck. So you might think that your odds are probability of spades, 13, plus probability of queen, that's 4. That gives you 17 out of 52. And you'd be almost right, except you have double dipped the queen. You've counted the queen of spades as a spade, and you have also counted her as a queen. And so you've double dipped once. And so when you have something where your pet groups overlap a little bit, like recall before we had clubs and diamonds, and those don't overlap at all. So we just added them together. Here, because they overlap, we just have to subtract out the one that overlaps. So here we're going to take our 13 out of 52 and add up to our 4 out of 52. But then we're going to subtract the one that overlaps, the queen of spades. So we're going to take out that 1 out of 52. That gives us a total of 16 out of 52. So that is our odds of pulling a spade or a queen. And that makes sense, right? If you imagine how many cards are a spade or a queen, well, you got 13 spades, and you got 3 more queens because the queen of spades is already pulled out of the deck. And so together that makes 16 out of 52. Okay. So let me get to this, which I think will be our last problem tonight. We'll do 2 problems maybe, okay? But I think this might be the last one. Okay, so this one says we have a college class consisting of 24 computer science majors, 16 marketing majors, and 20 finance majors. 2 students are going to be selected from at random. What's the probability that both students will be marketing majors? So first off, we got to decide desired over total. And then we have to decide, is the fraction going to change? Is it a dependent or an independent situation? Okay, so take a minute on this one, and then I will get started on it. Okay, so let's get started on this guy. Desired over total. So first we need to know how many total students are we talking about. Well, we've got 24 computer science majors, 16 marketing majors, and 20 finance majors. So that's 24 plus 16 plus 20 students. So that's 60 students. We're interested in only the 16 marketing majors. So the first one that we pull out, we've got an odds of 16 out of 60 of getting a marketing major. And we can reduce this. We divide this by 4, we get 4 out of 15. Okay. It's got a 4 out of 15 chance that our first pull will be a marketing major. Then we're going to do another pull. And we want both to happen, okay, so we're going to multiply because, again, our odds are going to get less and less, so we're going to keep getting marketing majors, okay? So 4 out of 15, but then our next time, we've got less students. We've got 59 students left, and only 15 of them are going to be marketing majors because we already pulled one out. So the odds that we will get both are 4 out of 15 times 15 over 59. Fortunately, these cancel, and we get 4 out of 59. So that is the answer. Okay. Cool. So next time when we come back, actually, yeah, next time we come back, there's one more probability problem here that you can do if you like. But next time we will do the rest of this, which is the universal accounting principle and the permutations. And then we'll finish up with all the geometry that we can cram into 3 hours, okay? So does anybody have any questions for me before we close up for the night? Seems like people are a little bit preoccupied or tired tonight. So I'm gonna shut her down and not run over. Any questions for me before we go? Nike, Lauren, Hema, anybody? Okay, so the homework for tonight, you do not need to go through the permutation and commutation. Yeah, no problem. Yeah, that's pretty clear. Tonight's a dead night. You don't need to do the permutation and combination stuff. Just if you see that, don't worry. It's not because you missed it tonight. It's not because you were like, spacing out. We didn't do it yet. Okay, so you can do any of the homework here, but the permutation combination stuff, just don't do it yet, unless you know how. That's great. Okay. Cool. All right, guys. Well, then I will sign out for the night. Thanks a lot for your attention, and I will see you again on Wednesday. Okay. So good luck with the homework, and I'll see you then.